quasicrystals, the reality as a lower dimensional projection of a higher dimensional universe. The universe is more than what it appears. All right. So really quick, let me just get into my notes really quick if you guys don't mind. Right. And so what we want to talk about is how quasi crystals are real. Right. These are like, so what we talk about are physical materials that were once thought to be impossible. So this presentation today uses them as concrete mathematical evidence that our 3D reality is a projection of a higher dimensional structure, not theory, but proof. All right? Not theory, but proof. So go ahead and light up because we finna take a little nice little journey today together. Together, folks. Are y'all ready? So, what are quasi crystals? Right? I'm quite sure you should be asking this question from the title of the show. What are quasi crystals? Right? So, first off, we got to start out with what is a regular crystal. So, a regular crystal like salt or diamonds, these are tiles, right? These tiles space in a perfectly repeating pattern, right? That's what they are. Tiles that space in a perfectly repeating pattern. Now, what makes a quasi crystal different, right, is that they're ordered and structured, right? They're ordered and structured, but the pattern never repeats, right? So we can almost compare this to a song that a song with a nice rhythm that you like, but there's never a chorus, right? There's no chorus, right? So there's like a song to a rhythm that you like, but there's no chorus. So this is something that was discovered in '82, right, 1982, by Dan Shechtman, who won a Nobel Peace Prize. But best believe he was very ridiculed, right? Because at one point in time they said that quasi crystals did not exist, only quasi scientists, right? So let's go into it. So we talk about classical crystal. I'm sorry, Christy, crystallography. I'm sorry. We talk about classical crystallography. It has strict laws, right? So these strict laws, only two, three, four, and six-fold rotational symmetry are possible in 3D periodic structures. Right. So a five-sided tile like a pentagon can't tile a flat surface without leaving space or gaps, right, in between. Yet when we start talking about quasi crystals, right, the quasi crystals show perfect five-fold, right, isosahedral symmetry in their diffraction patterns. This is mathematically forbidden in 3D, right, or in the three-dimensional, which is the first clue that there's something beyond 3D that it's happening, right? That's the first clue to that. So let's get into it. So when we start talking about higher dimensional solutions, right, we got to start out with the cut and project method, right? So with the cut and project method, no different than how we take a three-dimensional structure and we project it down into a two-dimensional structure so it can project through our TV, right? But what we're really getting in our through our TVs is a lower projection of an actual higher dimension, right? No different than that. It's the same thing when we talk about the cut and the project method, right? So let's get into it, right? The answer is the cut and project method. So you can imagine a six-dimensional cubic lattice, right? A perfectly regular repeating structure in a six-dimensional space. If you slice through it at an irrational angle and project the results in the three, and you can project the results in the three-dimensional, you get what's called a quasi crystal. The five-fold symmetry isn't impossible. It's just a shadow of a higher dimensional structure. It means our 3D reality is the shadow. The 6D lattice is the true object, right? So, meaning that what we see in our reality is actually a projection of the real world, right? Of the real world. This is actually a shadow world. Now, let's get into the mathematical framework, right? The mathematical framework. So, this isn't speculation. The math is rigorous and proven. Penrose showed in 1974, excuse me, that two simple rhombus tiles can fill a plane apparatically with five-fold symmetry. The key is that the tile frequencies are in the golden ratio. It's very simple. An irrational number, the signature of a higher dimensional projection. D. Bruijn formally proved in 1981 before quasicrystals is even discovered, right? That Penrose tilings are two-dimensional slices of a 5D lattice. The equation on the slide showed the projection map, right? As you can kind of see. So basically, at the center of a six-dimensional fold or six-dimensional lattice is a third-dimensional projection, right? That's what you get. So let's talk about physical evidence from nature, right? There are three independent lines of physical evidence that confirms this. Scretchman's 1982 electron diffraction showed sharp isosahedral spots. Sharp means long range order. Isosahedral means six dimensional, right? So anytime we talk about isosahedral, we still in the same game. We talking about six-dimensional lattices. Natural quasicrystals were found in a meteorite in 2009. These were showing nature produces them spontaneously. And then number three, don't forget, most powerfully, every single diffraction peak from every quasicrystal indexes perfectly onto a six-dimensional reciprocal lattice using integrals. No, no three-dimensional description works. The universe literally is storing quasi-crystal information in a sixth dimension or in six dimensions, right? Just think about that. The universe is literally, I'm going to repeat that. The universe is literally storing quasi-crystal information in six dimensions, right? In six dimensions. So what's the purpose? What is the information being stored in the other dimensions for? Just think about that, right? As we get into the holographic universe, physics already has a framework for this. The holographic principle. It says a higher dimensional space time can be fully encoded on a lower dimensional boundary. Projection. Remember the same way I told you. No different than you coding a three-dimensional uh, uh, um, uh, um, excuse me, basically you basically encoding a three-dimensional boundary or a three-dimensional code on a lower dimensional boundary, on a two-dimensional boundary. No different. The same thing is going on with the universe, right? So this is what we get when we start talking about the holographic universe. Quasi crystals are hands-on laboratory demonstrations of this principle, right? Physicist Gary Lissai proposed that the E8 lie, right, group or the eight dimensional contains all known particles and forces, and its lower D dimensions or lower D projections produce quasi-crystalline patterns. Physicist James Gates found error correcting codes in the map of the supersymmetry, the same codes used in computer chips. No different. Which is why we start to get into what? Are we inside of a simulation? You have to ask this question. Why? Because if reality is a projection from a higher dimension, right? That's structural identical to a simulation. Several features of physics point the same way. Energy is quantized, right? Discrete, like pixels, which is why I always ask people. I always ask. So first thing I say is, I say, "Yo, is our reality smooth or pixelated?" Notice they'll say pixelated. Nobody ever knows what that means. Like, bro, your TV is pixelated. You do understand that? So you're staring at me right now. The conversation we're having, your the display is pixelated. You're staring at tiny pixels, no different than our reality. Tiny pixels, which make it look like you're looking at one view, or which makes the display look smooth or appear smooth, right? But that's also perception. So when we get into this, right, we talk about quantum mechanics requires observation to collapse to a definite state, like on demand rendering, right? How do we know that? When we talk about the collapse, right? Quantum mechanics requires observation to collapse to a definite state. We know that from what? The double slit experiment, right? When as soon as when as soon as these elementary particles are observed, what do? They collapse into a wave function. I mean, into a particle force, so that you can't study the wave function, right? These are things that are programmed into our universe. So we talk about so and so we talking about it basically collapse into a definite state, and then the holographic principle places our 3D information onto a 2D or two-dimensional surface, right? Quasi crystals demonstrate all of this physically, right? They're complex 3D objects that are fully described by a simpler, higher dimensional rule set. Very simple, right? No other, it's no easier way or no better way to even explain what we're living in, all right? So let's talk about the theory of everything, right? The E8, right? Remember, that's the eight dimensional Lie group, has 248 dimensions of symmetry and is the most complex of the exceptional Lie groups. Physicist Clee Irwin quantum gravity research has shown that projecting the E8 lattice, or the eight-dimensional lattice, down to a third dimension produces point arrays that match the universe. Then all matter, energy, and forces are shadows of the eight-dimensional mathematical object, and quasicrystals are the visible, touchable proof that such projections even exist in nature. So just understand that, right? Understand that. So when we talk about, right, how the evidence converges, we got six independent pillars of evidence that converge on the same answer. Our 3D reality cannot be self contained. Quasi crystals require six dimensional mathematics to describe. The diffraction patterns only make sense in a sixth dimension. E8 projections reproduce them. The holographic principle predicts them. Whether you call it a higher dimension, a projection, or a simulation, the conclusion is the same. The universe is more than it appears, and quasi crystals are the proof sitting on a laboratory shelf. All right? That's just very simple. So, like, we tend to think of reality as everything there is, right? The three dimensions we can see, touch, measure, But quasi-crystals quietly change that assumption every time they're observed in a lab, right? So we got to think about this because they aren't exotic theoretical objects. They've been found in meteorites. They've been grown in laboratories, right? You can hold one in your hand, and yet, no matter how hard mathematicians and physicists try, they cannot fully describe what a quasi-crystal is using only three dimensions. The math only works when you add more. What that means is plain and simple, right? These patterns are ordered in our physical world that do not originate in our physical world. Simple. But if I get into my extraterrestrial bag, y'all say I'm jumping out the window. But we'll just keep it right here, right? Right. And so, like I said, these are things that come from this world, but they don't originate in this physical world, right? They come from somewhere beyond this physical world, a higher dimensional structure that our universe is, in some sense, a shadow of, right? So best believe we live in the shadow world. Think of a shadow on the wall, right? The shadow is real. You can see it, you can measure it, you can trace its edges, but it doesn't tell you the full story of the object casting it, right? Casting it. Our reality may be exactly like that shadow, complete and consistent on its own terms, but a projection of something richer, something we can't directly see, right? So we talking about quasi crystals. Quasi crystals aren't a curiosity; they're a crack in the wall, right? They're a place where the higher dimensional blueprint of reality leaks through into the world we can measure. And what they suggest is extraordinary, that the universe is not just in space. It is generated by a deeper geometric order that exists beyond it, right? That exists beyond it. We didn't build a telescope to see this. We didn't travel to the edge of the cosmos. We found the fingerprint of the higher dimension in a piece of metal on a laboratory shelf. Like, and so, I mean, at the end of the day, and I'm going to go ahead, man, and just end it right here.